This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
If you are using a symbol transistor amplifier, you don't have the effect of differential. The differential amplifier means a differential amplifier can cancel out noise. That property is not there. You can't make a ultra low noise amplifier. Then if you are using a transistor amplifier, you can't get lots of amplification because operation amplifier got multiple stages. Another thing is in the operation amplifier you can incorporate current mirrors in the operation amplifier. So when you incorporate current mirrors, you can make bias everything proper, and in the operation amplifier also you got output stage, so that you can increase the current, or you can do power, little bit power amplification, little bit current amplification at the output stage. So all these things combined together, then only you get a proper amplifier which can be used for amplifying very small signal. Not only that one, ideal operation amplifier got infinite input impedance. So your input impedance actually is very, very high for the operation amplifier, which you can't get with a simple transistor amplifier design. Infinite gain for differential input, very, very high gain, which you can't get again with a simple transistor amplifier. Almost zero output impedance, not possible with a simple transistor amplifier. Very high frequency bandwidth, again not possible with a simple transistor design. Then current going into the op amp is actually approximately equal to 0. For ideal amplifier it is equal to 0. Then CMRR, which is not possible to get with your simple amplifier, common mode rejection ratio. So that's the reason we have designed this operation amplifier. That is important. So that's the reason in the lecture I was designing the operation amplifier, and then we studied each block. Yeah, so I think all these are, as I discussed at the beginning, non-examinable material. Will not be discussed in the exam, means we will not ask any questions. But I will upload these slides so that you can go through it. And but I taught you because I want to make sure that you understood all the important concepts in the circuit design, especially analog design. And now I will go to my next lecture, that is the examinable part. We will be starting a new section, that is a frequency response.
I sent you an email yesterday night about the workshop function issue because did you check it?
Maybe I'll check it later.
Oh, okay. Because our partner, my workshop partner, didn't submit our report.
Okay. So I'll check it and email you.
Okay, thank you very much.
Yeah, that's it. Hello. Okay. Okay, yeah, because I'm going to start the lecture here, that's fine.
May I ask why, if I put a capacitor here, why this one is not a better solution?
No, this will do the amplification. This is a better solution. But then the problem is when you have a DC signal here.
Yes.
Then when you have a DC signal,
yes,
you want to amplify 0.02 millivolt DC.
Yes.
Then this amplifier will amplify DC.
No.
Why? Because why?
This cannot pass.
Yeah. So that's a problem.
Okay, that's a problem.
Yeah.
But for the AC, that's
AC, that's fine.
Okay.
So now we are going to start a frequency response, because frequency response is again important. As a design engineer, you should know frequency response. Otherwise, we will not be understanding much about the bandwidth, because you will be hearing the term bandwidth. What is the bandwidth of this amplifier? And then how bandwidth is changing when you add a capacitor. So because of these things, you should know frequency response. So that is the reason this is an examinable part. Oh, yeah, I'll be putting on the LMS. Yeah, thanks for letting me know. So when you take LM741, as I said, this is mostly a DC coupled amplifier, because otherwise what will happen is you can have AC coupling or DC coupling in the amplifier, but the operation amplifiers are designed in such a way that there is a DC coupling. You know what you mean DC coupling? DC coupling means, yeah, this is a DC coupling which I already discussed in the previous lectures. So those of you not here. So when you have two amplifiers, if you use a capacitor here, that is called AC coupled amplifier. AC coupled amplifier means this part is isolated from this part, but then only the signal, varying signal, you can amplify using this one. But then if you don't have this capacitor, it's called DC coupled. Then you can amplify even DC voltage. So operation amplifier we can use for amplifying AC signals and DC signals. But still, you can see some capacitor here. They have connected. So, but then this is not for blocking or any DC or anything. But then when you connect this capacitor actually in the LM741, it will affect the frequency response, means the bandwidth of the operation amplifier. So then if you got a requirement of connecting some capacitor even to your DC coupled amplifier, like you are designing a couple of stages, but then due to some filtering, you can use capacitor for filtering, but immediately you connect a capacitor to your circuit, an amplifier, it will affect the frequency response of your amplifier, means it will affect the bandwidth. So I will talk about the bandwidth later. So that is the reason we need frequency response. Then another interesting thing is, now you have characterized your amplifier, actually several amplifiers. Then how did you get to frequency versus, why did you plot gain versus frequency? What is your interest? When you plot gain versus frequency, why did you do that one for characterizing the amplifier? Because when you do gain versus frequency, then what you are doing is, here I am measuring, I am giving same signal, maybe 10 millivolt, 10 microvolt. And then the same signal, then I will be varying frequency from 0 to maybe 10 megahertz. Then what I will be doing, I will be plotting. So this is my frequency 0 to 10 megahertz. Then I will be checking the output voltage. Then I will divide output by input, because input I keep it constant, I only vary the frequency. So frequency is varied. When that is happening is, this is the gain. Then what you see is, you will never see a straight line like this. So when your frequency is increasing, then your gain will decrease like this. And then when the gain is decreased up to 3 dB, so if it is a logarithmic scale, so this is a 3 dB. When the gain is decreased by 3 dB, that is called your bandwidth of the amplifier. Bandwidth of the amplifier is a frequency, maybe this is 5 megahertz. So the bandwidth is 5 megahertz, means your gain is constant over that range of frequencies. After that, your gain is decreasing. So the standard number is minus 3 dB. So this is, here it is reduced to minus 3 dB. Then we call it that this is a bandwidth. And then that is a bandwidth of an amplifier. So in your amplifier also you got bandwidth. So did you find out bandwidth for your amplifier? How much was it? Yeah. Then the question is, how did you find out the bandwidth? You find out the bandwidth, you connected a same voltage and then you varied the frequency. Then what is the importance of this bandwidth? Because you will be using, first question, why sinusoidal signals are used for testing the bandwidth? Did you use sinusoidal or square wave? Sinusoidal. Why did you connect the sinusoidal signal, it's constant voltage, and then you varied the frequency of sinusoidal signal? Why you did not use square wave? Why you did not use triangular wave? Yeah, that's the answer. So the answer is, if you do Fourier analysis, so then you got the music. This is a music signal, and when you do a Fourier transform of your music signal, it is made up of so many sinusoidal signals of different frequencies. And then a real world signals are sums of sinusoidal components of having various frequencies, amplitudes and phases. And then that is the reason, though this signal you don't have many, you don't see sinusoidal signals, but this is made of so many sinusoidal signals of different frequencies. And then if this frequencies ranges from maybe 1 to 5 megahertz, an example, 1 to 5 megahertz. If it is ranges from 1 to 5 megahertz, then you find out from the Fourier transform. Then what is, so this is a frequency, sorry, yeah. So if it is 1 to 5 megahertz, then you have to, if your frequency components is from F1, 1 hertz to 5 megahertz, so that is the maximum frequency component, then you should be looking for an amplifier with the bandwidth, how much? Yeah, 5 megahertz or even bigger. Otherwise what will happen is, if you are taking a, so this is ideal, this is good, but then if you are taking another amplifier, this is a gain logarithmic and this is a frequency, but only your bandwidth is 2 megahertz. But then in your sinusoidal Fourier transform, you have got components of the music waveform. This is your music waveform, maybe something like this. And then the Fourier transform, when you take ft. So when you take Fourier transform, you are getting frequencies from 1 hertz to 5 megahertz. But then your amplifier got only bandwidth only 2 megahertz. Then what is the meaning is 1 hertz to around 2 megahertz, the sinusoidal signal will be amplified constantly. Maybe this is equal to say 100 value. So this range you get 100 amplification. So remaining sinusoidal frequencies 2 megahertz to 5 megahertz, your amplification is less than 100. Then what happens is, then when you put together means then inside the sinusoidal component, so many sinusoidal components are there. But then when you amplify, if you don't amplify uniformly, you will get distortion. So your signal will be getting distorted. So that's the reason you should have the right bandwidth. So in order to understand the bandwidth, you should know the frequency response. So that is the reason we are studying the frequency response. And then here we use the sinusoidal signals for testing the bandwidth, because when you take FFT of a real waveform like a music waveform, it is made up of so many sinusoidal signals. And so phone conversation difference from face-to-face conversation, you might have noted. Why? Because your natural voice is 20 hertz to 20 kilohertz. That is our audible range, the voice, the frequency range. But like you talk to someone, and then when they talk over the phone, the sound might be slightly different. Why? Because when somebody is talking, it may be from 20 hertz to 20 kilohertz range, but then your phone got only finite bandwidth, maybe 400 hertz to 3.5 kilohertz. So then you are throwing away some frequencies. Then what will happen is your sound may be a bit different. That is the reason. That is a big challenge in the audio amplifier industry. So audio amplifier industry is still kind of emerging. New companies are coming. Why? Because audio amplification is a big challenge, because you can't make an amplifier in this range working properly. So then that's the reason you have got a different 2-3 amplifiers in some speaker. One speaker dedicated for some small range, another speaker another range, like that. So audio amplifier design is actually a bit complicated. So if you got limited bandwidth, what will happen is your sound may be a bit different. So natural human voice spans a frequency range from 20 hertz to 20 kilohertz. However, conventional telephone system, old ones, passes frequencies from only 400 hertz to 3.k hertz. But then the recent ones got a much better bandwidth than this one. Then again, the way you hear your voice is different, because I hear my voice differently than you hear my voice. Why? Because the path traveled by human voice to the voice recorder. So from my mouth, it is going to the ARC, then I got the recorder. But then how I hear is mouth, then the sound is passing through the skull and the ear. So the skull passes some frequencies more easily than others, because skull got, again, is actually like a filter of sound waves. not electrical, because from the skull the sound is passing through. So the skull got some kind of filtering effect. It can pass some frequencies more easily than others. Since the paths are different, the result will be different. So that is another example of a kind of a frequency, it is affecting how it is passing through. Again, in the video signal, if you got a graphic card and then you got a 5 megahertz bandwidth, then you are going to display it. If you got a high bandwidth, then your signal will be, you can see like clearly. If you got a low bandwidth, you will see this type effect. So video signals without sufficient bandwidth becomes fuzzy, as they fail to abruptly change the contrast of pictures from complete white into complete black. That is the pixel switching on and off. So even in the video, the bandwidth is very important. So that's the reason you are going for NBN, higher bandwidth, and amplifier, you are buying higher bandwidth amplifier so that you can amplify all the frequencies. Then now we are going to look at the frequency response. So this is a simple low pass filter. So simple low pass filter means you got a voltage signal, then you got a resistance, then capacitor is connected between this resistance and ground. So when you have different frequencies here, then with the same amplitude, then you can find out the gain. So if you put V out by V in, then what is happening is your V in, if it is 1 volt at low frequencies, here you get 1 volt. That is the reason here the amplification is 1. When the frequency increases, what is happening is your gain is kind of constant, then it started decreasing. So it is called a low pass filter. So this is called a low pass filter. Why? Because it is passing only low frequencies and blocking high frequencies. And this point is maybe 3 dB point. So V out. How to write down V out when there is a capacitor? V out equal to impedance of this capacitor. So that is the equivalent of a resistor with a frequency dependent resistor, that is called impedance. And then here you got impedance of the capacitor that is coming in parallel with the R1. So your V out equal to impedance of the capacitor into input voltage divided by R1 plus ZC. So what is ZC? ZC equal to 1 by 2 pi FC, which you already know, which always people always write like sometimes omega C. Omega is 2 pi F. F is the frequency, C is the capacitance. In the textbook, they write 1 by CL into S. So I am using this notation instead of omega C because in the Rasavi's textbook, if you are reading Rasavi's textbook, Rasavi is using instead of omega C, CL into S, this notation. So that's the reason I have included this one to be consistent. And then how to prove this one is a low pass filter. So from this equation, if you know the output, so or output by V in, that is a transfer function. So output, so in the electronics, when people are talking about transfer function, means mostly it is output by input. So that is a transfer function in electronics. Then if you know the output, you can prove that this is if you know the expression for output in terms of V in, when there is a capacitor, you can find out whether it's a low pass filter or high pass filter. So how to find out is you can put first F tends to 0. So if F tends to 0, what will happen? If F tends to 0, your impedance ZC tends to infinity. When if ZC tends to infinity, what will happen to V out? So ZC plus R1, ZC is a very big value, then ZC will stay there. ZC and ZC will cancel out. V out equal to V in. So that's the reason we are getting kind of 1. And then F, so F is equal to infinity means then ZC tends to 0 here. So that you are getting very small value. So that's the reason it started decreasing. So when you apply these two conditions, then you can get some idea, you can understand whether it's a low pass or high pass. In this simple example, as frequency increases, the impedance of C1 decreases. So that's what we see. And the voltage divider consists of C1 and R1, attenuates V into a greater extent at the point. So it's a low pass filter. So when frequency increases, what is happening? It is passing the R1 and it is coming here, but it is not going to this point. That's what is happening here. Then where it is going? From this point it is not coming, then where it is going? Yeah, the capacitor will be shorting to the ground, all the high frequency components. So this is an example. So you designed an amplifier. Maybe when you connect a speaker or a load, that one got actually an input capacitance. So whatever you connect, that one got impedance, output impedance, and then that one also got some kind of capacitor. Because this is made of electronics, then there will be some capacitance. And then if that is CL is a capacitance, and then we can get the small signal. So when you get the small signal V in, and then this part is open, then you got GM into V in, and then you got RD connected to the ground. And now we take into account CL. Usually CL, what is CL? In the small signal we short the CL. You know what I meant, capacitor. But if you want to find out the frequency response, you have to include the CL in the small signal. Then you might ask in the exam how we will know. In the exam, we will clearly mention in the question if you have to take into account the CL. You know what I meant? So there is no confusion. Then in the small signal, in the real life world, if you want to find out the frequency response of your amplifier design, you have to take into account the capacitor in the small signal diagram. Otherwise, capacitor is a short in the small signal. And then if you want to find out frequency response, you have to take into account this capacitor. We know that without taking into account CL, gain equal to minus GM into RD. Now we are going to find out if you connect this amplifier output to maybe some speaker or some other output, but then that device got an capacitance, input capacitance of CL, then you are driving some capacitor CL, then you want to find out what will happen to this gain. Because if you got a capacitive load, if you got a capacitance, then you want to know what will happen to this equation. Then you can draw the small signal. And then, so this one is equivalent of RD parallel with the impedance of the CL. Impedance of the, which is equal to RD parallel 1 by CLS, which I already said, which is equal to 2 pi F into C, which we represent. Because we are this is actually an impedance, a resistor whose value is depending upon the frequency. So that is an impedance of the capacitor. So your V out equal to output current into R out, which is equal to minus GM into V in, that is your output current, into R out. So your R out, when you look from here, you see the parallel combination. See, minus GM V in into RD parallel 1 by CLS. So the capacitive load CL is the culprit for gain roll-off, since at high frequency it will steal away some signal current and shut to the ground. So here what we are talking about CL is, in this expression, gain equal to minus GM into RD for this one. And then as per this equation, what is a bandwidth? Of this amplifier? As per this equation, minus GM into RD, so what is the bandwidth? 0. How many of you think? Infinity. Yeah, so as per this equation, your bandwidth is infinity, but that is not correct actually in the real world. And then when you connect to maybe another capacitor, capacitive load, what will happen is this will definitely affected. Even this will be affected, actually this will be affected by internal capacitance of this transistor, which we have not taken into account. So that we will study, because low frequencies, that will not play a major role, but if you got any capacitance in the circuit, this value will be affected. The best example to prove that is when you have a capacitive load, then what will happen is your frequency suddenly bandwidth will suddenly decrease to this value when you connect a capacitor. So this is an example, a capacitor or a capacitive load can affect your frequency response. Then if you are interested in the equations, this is the transfer function, the general equation, and then this is the transfer function, this A0 1 plus j omega by omega z1, and then A0 is the low frequency gain, that is equivalent of your minus GM into RD. So this is called a low frequency gain, minus GM into RD, what we derived. And then omega ZJs are zero frequencies, omega PJs are pole frequencies. We will be studying pole in the coming lectures. And then if the if S tends to 0 here, then HS become A0, means at low frequencies, means S is a frequency. If frequencies tends to 0, then your gain will become A0. Means in the electronics, as I said, the transfer function means V out by V in. That is a transfer function. So then here V out by V in will go to the low frequency gain. That is this minus GM into RD. So in the small signal, when you do, why it is called a small signal gain? Minus GM into RD is called small signal gain. Why? Because when you calculate, when you derive your small signal expression, actually you are not taking into account the effect of capacitor. So that is the reason small signal gain. Then why we are not taking into account, how can we say that is a small, this gain is a low frequency gain? Definitely we are not taking into account the capacitor effect when you calculate this gain. Yeah. So low frequencies, your capacitor is kind of open, so you don't have to take into account capacitor. So that's called a low frequency gain. Then which capacitor? So there is a lots of capacitors in the transistor itself. Between base and the emitter there is a capacitor, because you got a capacitor if you take PN junction. Between collector and the base, between base and the emitter, lots of capacitance are there. These capacitance we taken as open. Why? Because at low frequencies your capacitance is, that capacitance value is very small. That capacitance we taken as open at low frequencies. High frequencies, what will happen is these capacitance will come into effect. So that we are going to derive the gain at high frequencies. If you take into account those, means this is fine at low frequencies like 10K, 20K, but if it is 1 gigahertz, then we have to take into account these capacitances between base and the emitter. So that is the reason this is called a low frequency voltage gain, because we don't take into account any of the capacitances because they are open at low frequencies. Yeah, then this is a equation, standard equation. How it is related to our equation is that this is equivalent of V out, means, sorry, this is equivalent of our gain, V out by V in, transfer function. In electronics is V out by V in, and then that is equal to low frequency gain when you have frequency tends to 0. And then if the input to the circuit is a sinusoidal of the form, then we can write xt equal to a cos into 2 pi ft symbol, a cos omega t. Then the output can be expressed as yt equal to a into h into j omega. J is the complex number, cos omega t plus h, this one, and then s equal to j omega, which is equal to j into 2 pi f, which we already discussed in the previous slide. And then this is a magnitude, this is a phase. So that's this notation comes. Yeah, so we will come to the electronic aspects, because we are going to look at the transfer function from the electronic side. Now, determine the transfer function and the frequency response of the common source stage here. So you got a capacitor connected here, maybe coming from the load. How to find out the transfer function? How to find out the frequency response? In order to find out the transfer function, you have to draw the small signal. In the small signal, you have to incorporate the capacitor. Then you can find out V out, which is equal to output current into R out, which is equal to minus GM into V in RD parallel 1 by CLS. Transfer function, V out by V in, then I have written here bracket S, means by S, because this is a function of frequency. So that's a transfer function. So transfer function is in the electronics is the V out by V in, which is a function of frequency or frequency dependent gain, which is equal to, here you got minus GM RD parallel 1 by CLS. So then you got the transfer function. Then now I am going to expand it, because minus GM into RD parallel 1 by CLS, which is equal to RD into 1 by CLS divided by RD plus 1 by CLS. Parallel combination I am expanding. Then rearrange minus GM RD divided by RD into CLS plus 1. For a sinusoidal input, we already said S equal to j omega. For a sinusoidal signal, S equal to j omega actually. So then we can write HS transfer function equal to minus gm into RD by RD CL j omega plus 1. If you take the modulus, then what will happen is gm into RD, then modulus of a complex number, root of R square CL square omega square plus 1. So omega equal to 2 pi f. If at omega equal to 1 by RD into CL, if you put this omega that is equal to 1 by RD into CL, then I can write V out by V in magnitude equal to gm RD by root 2 if at omega equal to 1 by RD CL. So then that is a frequency response. We already got the frequency response. So then omega equal to 1 by RD into CL, your gain is gm RD by root 2. So that is so then what you are finding is your low frequency gain is equal to minus gm into RD. At omega equal to 1 by RD into CL, your gain is reduced by gm RD by root 2. So you are getting that type of response. Then we will be talking more about one in the later. Then why we are using log? So most of the time what we will do is when you derive frequency response and then we plot it. When we are plotting, we will be using logarithmic scale. So in general, why do we use logarithmic scale? In the logarithmic scale, there is an advantage. That's the reason. So let us consider two amplitudes A1 and A2 respectively. The ratio of these two signals is A1 by A2. Because we often deal with the ratios that change by many order of magnitude during a testing procedure, then means somewhere it is change is maybe 2, somewhere it is 50, somewhere it is 100, somewhere it is 1000. Then if you got logarithmic scale, you can all represent in a single graph. So that is the reason we use a logarithmic graph. So that is the reason the frequency response also, the changes are big, then we will be using A1 by A2 dB, which is equal to 20 log A1 by A2. That's why we get logarithmic response. So here we are getting V out by V in the previous expression, gm RD by root of R square RD CL square omega square plus 1. At omega equal to 1 by RD into CL, what you are getting is gm RD by root 2, which is equal to 0.7 times gm into RD. That is gain decreased at 1 by RD into CL. So if you take logarithmic value 20 log 0.7, which is equal to minus 3 dB. So that's how we get to this idea of minus 3 dB. So what it says is here what we have observed is so you got the low frequency gain that is equal to minus gm into RD. So that is your low frequency gain. So amplitude equal to gm into RD. So this is a frequency, this is a gain. Then gm into RD, that is a gain. But then from the transfer function at omega equal to 1 by RD into CL, what is happening is your gain, which is equal to gm into RD divided by root 2. At this point, omega equal to 1 by into RD CL. So this omega equal to 2 pi f means, so that's the reason this frequency. Maybe that is this point. So that's why happening is it is coming like this. Gm RD by root 2. So that is your new value. At this omega equal to 1 by RD into CL. You know what I meant? And then if you represent this in the logarithmic scale, if you put log f and then log of AV, when you plot it, when you take a logarithmic value and then this point omega equal to 1 by RD into CL, this decrement is minus 3 dB. So the minus 3 dB, that's the reason we often tell the minus 3 dB point is because we take a logarithmic value, this gm RD by root 2, that is equal to 0.7 into gm into RD. When you take a logarithmic value, minus 3 dB is the point. So V out by V in dB drops by minus 3 dB at omega equal to 1 by RD into CL. So that is the frequency response. You know what I meant? So it is actually gm RD by root 2, 0.7 gm RD, that is the actual reduction in the value, means it became 70%. But then when you take a logarithmic value, that is equal to minus 3 dB. So that is the reason the minus 3 dB is coming into picture when you talk about the bandwidth. Then frequency response. And then V out by V in gm RD by R square D C square omega square plus 1 at omega equal to 1 by RD into CL, your gain reduced by gm RD by root 2. So that is a minus 3 dB. So that's the reason that is the bandwidth. And then minus 3 dB roll off. So this is minus 3 dB roll off. At low frequency, the capacitor is effectively open. So why it is happening, we already understood the concept. The capacitor at low frequency, what is happening is this capacitor is kind of open. Why? Because low frequency impedance is very high. But high frequencies, what will happen is when the frequency is increasing, then it is kind of passing the signal to the ground. So your gain is decreasing. As the frequency increases, the capacitor tends to short and the gain starts to decrease. Short means shorting the high frequency components through it. A special frequency, that is omega equal to 1 by RDCL, where gain drops by 3 dB. So that is the acceptable limit. At omega equal to 1 by RDCL, up to here, all the frequencies are kind of amplified uniformly. So that is the reason we are taking minus 3 dB point. Before that, all bandwidth. That's the definition of bandwidth, before minus 3 dB point. Then we represent your frequency response in the body plots. Then the transfer function of a circuit, again, this is the transfer function which we already discussed. Rules for getting a body plot magnitude versus frequency plot. When we hit a 0, this omega Zj, the body plot magnitude rises with a slope of 12 dB per decade. When we hit a pole, omega Pj, here this one, body magnitude falls with a slope of minus 20 dB per decade. How many of you studied body plots in the previous, yeah, you all studied, I think Melbourne system, I'm pretty sure you already studied body plots. So what body plots tell is, when you talk about zeros and poles, then what they are talking about is when you have when you represent this logarithmic value of gain, logarithmic value of the frequency, that is called body plots. When you plot your gain versus frequency, this is called actually a body plot. In the body plot, you might be seeing some, so in the body plot is something like this. It is coming, and then your body plot is gain is coming. Then what I said is, what is a 0? 0 means suddenly frequency response increases like this. And then this slope is plus 20 dB per decade. Then we call it as, this point is a 0 or pole? 0. Then this is going like this, and then suddenly it decreases like this by minus 20 dB per decade. So this point is a pole. This point is a 0. So in the frequency response, when from here it is suddenly increasing, the slope is 20 dB per decade, then we call it as a 0. If it is decreasing like this, that is called a pole. So that is a simple meaning to understand this. Then here, when you plot it, when you take logarithmic scale, then this minus 3 dB roll off, actually that is 20 dB per decade when you plot it. So then this is a pole or 0? How many of you 0? Pole. Okay, I'm happy that you are not sleepy. This circuit has how many poles? Only one pole here, yeah. Non-zero at no zeros. Means we don't have zeros, means not the literal 0, the 0. Because pole and 0, we don't have that 0 where the slope is increasing 20 dB per decade, plus 20 dB per decade, we don't have that 0. So we have only one pole, not zeros, at 1 by RDCL. So the slope drops from 0 to minus 20 dB per decade as we pass through omega P1. Pole identification example. So here you got two capacitances. One is Cin, another one is Cl. Cin is the input capacitance of your maybe your MOS. Cl may be coming from some load. So then we have to identify the pole. So why do we need to identify the pole? Because if you identify the pole, you know that where your frequency response is suddenly changing. Okay. Then how to identify the pole? Omega P1, which is equal to 1 by RC into Cin. Because if you look at here, when you have a resistor here, when you have a capacitor here, then your pole equal to 1 by RD into CL. See, it's straightforward. Same way, here we can say, so here it is equal to 1 by RS into Cin. Then how about here? 1 by RD into CL. Because here, which we already proved, so that's how we find out. Just get the resistance capacitance. And then this one is a low pass or high pass filter. So then you can, sorry. Yeah, then so we got the circuit here, and then easily we can find out omega P1, which is equal to 1 by Rs into Cin is a low pass. Here it's equal to 1 by Rd into Cl. And then if you want to find out the equations, transfer function, we can draw the small signal. Rs, then Ci, that is Cin, input capacitance, and then V1 between this gate and source. Then you got Gm into V1, then you got Rd, then you got Cl. Now, how to write down the equation? What is the value of V1? If this is V in, yeah, V means we have to take into account the impedance of this capacitance. So then V1 equal to 1 by C in S into V in, or 1 by C in S equal to 1 by 2 pi FC in. So we represent it as C in S plus Rs plus 1 by C in S, because that is a voltage here. Then your output equal to output current into output impedance, which is equal to minus Gm into V1 into Rd parallel 1 by CLS. Then you already got the value for V1, so you can substitute V1 here. So when you substitute V1 here, your V out equal to this V out. This is a V1 from this one. And then you already got to V out and then V in here. So you can take V out by V in, your transfer function, minus Gm into 1 by C in S V in by Rs plus 1 by C in S into, sorry, here one parallel is missing, Rd parallel 1 by CLS. So you can expand Rd into 1 by CLS plus, sorry, divided by Rd plus 1 by CLS, you can rearrange, and then you get 1 plus Rs into C in S, 1 plus Rd into CLS. And then which we can write it as minus Gm into Rd into 1 plus Rs into Cs, what is, if it is a sinusoidal signal, S equal to j omega. So that is S equal to j omega, S equal to j omega here. Then, which we can write it as, when you take modulus, what will happen is GMRD and then root of 1 plus omega square by omega P1 square, we can write it like this. Because Rs into C in, what is Rs into C in here, which is equal to 1 by omega P1. Rd into Cl, which is equal to 1 by omega P2. So we can substitute here. So then that is this is a transfer function. How many poles here? Here 1 by Rs into Cin, another 1 by Rd into Cl. So pole identification example, a group work. So this one is, we already identified the pole, which is easy. Then the whole point in identifying the pole, now you know the meaning. Why do you want to identify the pole? We don't identify the pole without any purpose, because if you identify the pole, what you are seeing is in the frequency response, we know that, oh, there is a frequency, the gain is decreasing. Like the whole point in identifying pole is, when you want to find out, you might be thinking your frequency response in the log f, then log V out by V in, you might be thinking your frequency response is maybe like this. But then if you find out all the pole, then you will understand maybe this point you are getting like this, and then maybe then will stay here, then maybe again it will fall like this, and then this may be minus 20 dB per decade, this will be minus 20 dB per decade. You know, that's the reason we are identifying the pole. How many points are there in your frequency response where your gain will decrease by minus 20 by dB decade? So we want to find out. So that's an entire point in, sorry, finding out the pole in the circuit. Yeah, so if you want to cancel out the pole, so his question is, suppose you got the frequency response like this, then there are many ways we can get rid of this one and make it maybe a bit more like this. For that, what we'll do is, here if we introduce a 0, then this we can cancel out. When you introduce a 0 at this point, it will be like this. Then this will add up and you will get a straight line here. And then here also you can add, if you introduce a 0 here, then you can make again this straight. You know what I mean? So poles and zeros can be cancelled, well, which we will not be studying here. But then, you know, that is another big topic in the frequency response, cancellation of poles and zeros. Now we are identifying pole because that is important for the amplifier design, because we don't want your gain suddenly dropping. We want to find out where, you know, that is dropping and how it is dropping. The pole of a circuit is computed by finding the effective resistance and capacitance from a node to the ground. See, if you got a node to the ground, easily you can write down what is the pole here. Yeah, pole is 1 by Rs into Cin, because you got the resistance value, you got the capacitance. Then here, how to find out? easy. Your capacitance is from node to the ground. See, 1 by RD into CL, then it is easy to write down the pole, where the pole is occurring. We can find out omega. If you know omega equal to 2 pi f, then you can find out what frequency. But then, how about this circuit? If you got a capacitor like this, how can you write down the pole and zeros? Yeah, Rs into 1 by Rs into Cf, that is for the input pole. Then output pole also, then what is Rd by Cf? You get both same. So there is a problem. Sorry? Yeah, but then this capacitor is, this is only applicable when effective resistance, when it's from node to the ground. When your capacitance is from node to the ground, this is correct. But here you don't have a node to the ground. This is a node, this is a node. So then the circuit above creates a problem since neither terminals of CF is grounded. A method is required that transforms a floating capacitor into two grounded capacitors, thereby allowing the association of one pole with each node. So then if you got a floating capacitor, we have to develop a technique that will allow us to split this capacitor, and then some will come as the input, some will come in the output. But then how to split it? So then the splitting is called Miller's theorem. So Miller came up with some idea, because this became a kind of a problem. Then the Miller came up with an idea, a simple technique that is called Miller's theorem. In the Miller's theorem, what Miller says is an interesting concept. So suppose you got some impedance between 0.1 and 0.2. So that is an impedance ZF, and the voltage is equal to V1, and then here the voltage equal to V2. Then what Miller says is, we can split this ZF into two, and then this part can be open. Then Z1, then the Z you split it, and then you make it this Z1, and then keep the voltage same, and then make it Z2. And then if I can do the splitting only if one thing is done. So maybe what Miller says is the following. Maybe I should draw it, then only you will be able to appreciate what Miller did. So then you got 2 points. So this is a box. Okay, in the box you got maybe a resistor, and then you have connected here maybe 1 volt. Maybe you have connected here, then you are getting maybe X volt. Maybe I'll say this is X volt, and then this is 1 volt. Then you are getting some X volt. We don't know. Then we know that here there is a resistor, and then the current going is, you already measured it here. That is equal to maybe 5 milliamps. So this is a box. Then this is a one. Then I just closed the box. Then how do you know this resistor is here or not? Because you got 5 milliamps here. But then if what I do is, in the box you can't see, I will split this one. Then what I will make sure that I may do, maybe this I connect to the ground, and then this ground again, this is the ground, then I connect another one and then come here. If 5 milliamps is going in, you won't be able to see whether I split or not. You know what I meant? If I do some adjustment to this value, if I do adjustment like value, if I get 5 milliamps is going in, maybe X milliamps is coming in. Then if same X milliamps is coming in, you are getting here X volt. If you are getting 1 volt, you don't know whether I split or not. So maybe we can split it. But provided same current should go in, same current should come out. That is what Miller did. So Miller did, it is possible you can split it, but then only thing you have to be careful is the currents going in should be same. Same current should come from here to here, same current should come from here to this point. That is called Miller's theorem. If that is the case, what Miller says is V1 minus V2 divided by ZF. V1 minus V2 divided by ZF, and then that is should be equal to V1 by Z1. You know what I meant? The current. And then which should be equal to minus V2 by Z2. Maybe in my drawing it is pretty clear, because here you got it. So here 5 milliamps means 1 volt minus X volt divided by, maybe this is R, which is equal to maybe, so here 5 milliamps is going, here also 5 milliamps is coming out. So which is equal to 5 milliamps. You know what I meant? Because 1 volt minus x volt divided by R equal to 5 milliamps. I can split it. You wouldn't notice whether I splitted it. If this is R1, this is R2. If what happens? This 1 volt minus this one, whatever this one, maybe Z by R1, that is equal to 5 milliamps. So I should make sure that 5 milliamps will go from here and then 5 milliamps come from here. In that case, you won't be able to understand whether it is split or not. So that's what Miller says. What Miller says is here, if you make V1 minus V2 by Z which is equal to V1 by Z1, that is equal to, that is this current. So this current is V1 minus V2 by Z is this flowing this one. You can split it, but then between this point and this point also you should have same current, which is equal to V1 by Z1. Then from here also 5 milliamps should come up. Then only when you look here 5 milliamps is going in, when you look here 5 milliamps is coming out. So when you look in 5 milliamps is going in, if you can make V1 by Z1 equal to 5 milliamps, your value should be Z1 in such a way that 5 milliamps will go from this point to the ground. When you look here 5 milliamps should come up. Then your Z2 should be such a that minus V2 by Z2 because it is coming from ground to this point. So that it is equivalent of connecting ZF between these 2 points. Then we can find out what is the value required for Z1. If you want to make that arrangement, your Z1 should be equal to ZF into V1 by V1 minus V2. Then your Z1 equal to ZF into, you can substitute V1 minus V2. So here we can substitute which is equal to 1 minus V2 by V1 because V2 by V1 equal to AV. So which is equal to Z1 should be ZF by 1 minus AV. Then same way you can find out Z2. Z2 equal to ZF into minus V2 by V1 minus V2. So if you got ZF, some impedance here, then you can split this into 2 and then connect to the ground, and then this also you can connect to the ground. Then your Z1 should be ZF by 1 minus AV. AV is the gain of the system here if you got some gain. And then Z2, ZF into minus V2 by V1 minus V2. Then you can split it as I discussed. The same current is going, same current is coming in. So that is called Miller's theorem. If AV is the gain from node 1 to 2, then floating impedance ZF can be converted into 2 grounded impedance Z1 and Z2. We will continue in the next lecture.